Hey everyone, welcome back to this channel. So for today we're going to dive into a topic that's all around us, from the social media we use every day to the GPS in our cars, and that's the graph theory. So before we jump into it, let's first take a quick look where it all began. Tracing back to the 18th century with a guy named Leonard Euler, he was basically trying to solve a famous puzzle called the Seven Bridges of Königsberg. So the puzzle basically asked if it was possible to walk through the city and crossing each of the 7 bridges exactly once and returning to the starting point. So here Euler modeled the land masses as points and the bridges as connections, so which essentially created the first known ever graph representation. And then later on he proved that it was impossible, and in doing so he laid the groundwork for this entire field of study. Pretty cool, right? So what exactly is a graph? So according to Reinhard Distil's The Graph Theory, 5th edition, 2017, he defined a graph as an ordered pair of V and E, where V is the set of vertices and E is the set of the edges. So in the example, we have a set of vertices from V1 to V6, and we have a set of edges from E1 to E6. The diagram illustrated above is a visual representation of this definition. So the vertices are the black dots and the edges are the lines connecting them. Now graphs come into two types. So we have the undirected graphs, where the edges are just connections without specific direction. And here a great example could be friendships on Facebook. So if you're friends with someone, the connection goes both ways. On the other hand, we have directed graphs. So here the edges have clear directions, and a perfect example would be like Twitter. So you can follow someone, but they don't not necessarily have to follow you back. Now, why should we care about this? Well, graphs are pretty much everywhere. For example, in the social networks. So the social media platforms like Instagram and LinkedIn are basically giant graphs. So the logic behind this is that the users are nodes and the connections between them are edges. Second, the transportation networks. Have you ever wondered how GPS finds the farthest route? It's all thanks to the graph theory. Cities or intersections are nodes, and then the roads are the edges. Last but not least, it's the supply chain management. So businesses use graphs to model their supply chains to optimize the flow of goods. The factories, the warehouses, and the stores are nodes, and then the transportation routes are the edges. When it comes to implementing graphs, we usually use one of the two main representations, and the first one is the adjacency matrix. So this method represents a graph as a square matrix where rows and columns corresponds to the vertices, and here an entry in a matrix says at the position. In the example above is the undirected graph. So here we have a graph with 5 vertices, and they are labeled from 1 to 4, and the edges connecting them. So here in our matrix, we are going to have rows and columns labeled with the vertex numbers from 0 to 4. And a value of 1 in the matrix means that there is an edge between the two corresponding vertices. Otherwise, a value of 0 means that there is no edge between them. For example, if you look at the intersection of row 1 and column 2, the value is 1. This corresponds to the edge connecting the vertex 1 and vertex 2 in the graph. Similarly, the value at the intersection of row 0 and column 2 is 0. So this basically indicates that there is no direct edge between vertex 0 and vertex 2. Now let's see another way graphs could be represented, and that way is the adjacent list. So this basically represents a graph using an array of vertices and an array of edges, where each vertex stores the starting index of its outgoing edge. Adjacent list is basically like a collection of lists. So each list has to store vertices that are directly connected. So the main vertical column on the left represents the vertices from 0 to 4, and the boxes to the right of each number are linked lists that holds their neighbors. So like for example, for vertex 0, the list contains 1 and 4 because vertex 0 is connected to both 1 and 4. And for vertex 1, the list contains 0 and 2. Vertex 2, the list contains 1 and 3. And the vertex 3 list contains 4 and 2. For vertex 4, the list contains 3 and 0. So because this is an undirected graph, so each connection appears in two places. So like both vertices list the other as the neighbors. For example, 0 is in 1's list and 1 is in 0's list as well. So this is a common way to like store graphs that are in computer science, especially for graphs that are sparse or like have fewer edges than possible. However, my opinion, so while the adjacency matrix is simple and quick way to check if two vertices are connected, it can be really inefficient for large and sparse graphs because it wastes a lot of memory storing all the zeros. So adjacency list is more memory efficient for sparse graphs because it only stores the connections that actually exist. So now let's take a look at the graph traversal. So graph traversals are algorithms for visiting every node in a graph. And the two most common fundamentals one can use are the breadth first search and depth first search. So in depth first search, which I like to call the DFC, so this algorithm basically explores as far as possible down one path before backtracking. So it's like navigating a maze by going as deep down one path until you hit a dead end and then turning back. Whereas in the breadth first search, which I like to call the BFC, this algorithm explores the neighbors level-wise, like the layer by layer. So it's like dropping a pedal in the pond and watching the ripples expand the outwards. So you like first explore layer by layer of the neighbors. So below there is an example of a graph with 8 vertices from 0 to 7. And for the BFs, start from the source node, which is 0, and then we go down to 1, we visit 2, we go 3, and then we go down to 4, we visit 5, 6, and lastly we visit 7. So on the other hand, for the DFC, we are going to first start from the source code, we go to 1, and then we go downwards to 4, and then we go to 5, we go upwards to 1, but 1 is already visited, so we're not going back to it. We go back to 0, which is already visited, we're not going back to it, but we're also going to go to 2, so we are not going to visit 0 again. Instead, we're going to go down to 2 and then visit 6. We go upwards to 2, which is already visited, we go upwards to 0, which is already visited, we visit 3, and lastly we visit 7. So now this brings us to Dijkstra's algorithm. So Dijkstra's algorithm is a popular and efficient algorithm used to find the shortest path between the two nodes of a graph. So it's particularly useful for graphs where edges have non-negative weights or cost, and I like to think of it as finding the quickest route on the map when like roads are the edges and the cities are the nodes. So now this is how it works. So the first step, we have to maintain a dist array, which we have to initialize to 0 for the source node and then the infinity for all the others. And then we used a mini heap for P and Q to store the weight and the node as a pair. These are basically like the pairs for selecting the minimum and processed nodes. Therefore, we are going to push 0 in the source into the heap to start from the source node. And then second, we're going to pop the top element from the heap, like for example 0, 0, where u is equal to 0. And then for each adjacent node v of u, if the dist array of the element v is greater or equal to dist array element u plus the weight, and then we're going to adjust the dist v element to dist u element plus the weight and push dist, and then push the dist v element and v into the heap again. So here the core steps are basically like we initialize the distance value to every node in the graph, and then the source node's distance is set to 0 and all other nodes are given a distance of infinity. So you select the unvisited node with the smallest known distance and mark it as visited. And then here for each newly visited node's neighbor, it has to calculate the distance from the source node to that neighbor. So if this new path is shorter than the previously recorded distance to that neighbor, the distance is updated. So the process is repeated until all nodes have been visited. Now let's try to understand another concept of finding the strongly connected components. Now one can ask what a strongly connected component is, and here I would say that this is a part of a directed graph where each pair of the vertices is mutually reachable. And what does this mean? So this means that for any two vertices, U and V in the component, you can get from U to V and from V back to U by following the directed edges. For example, in the example, we have a directed graph with two main strongly connected components enclosed in the dashed circles and a single vertex that's also a strongly connected component. So the first strongly connected component is the vertices for 0, 1, 2, and 3. And this is a strongly connected component because you can travel between any two vertices within it. Like for example, to get from 0 to 2, you can follow the path like from 0, 1, and 2. And then to get back to 2 from 0, you can follow the path of 2 to 3 and to 0. The second strongly connected component is the component of 4, 5, and 6 vertices. So similarly, you can get from any vertex to any other vertex in this group. Like to get from 4 to 6, you can go from 4, you go to 5, and then you go to 6. And to get back from 6 to 4, you can go from 6 to 4. And then last but not least, we have a single vertex with no outgoing or incoming edges to the strongly connected component, which is also considered as a strongly connected component. It is mutually reachable with itself. And this brings us to a popular algorithm, which is the Salgorithm algorithm, which is used to find the strongly connected component in a directed graph. So it's a key algorithm in computer science for analyzing a structure of basically directed graphs. And it has two main steps or phases to follow. And the first one, you have to perform the DFC on the original graph. So basically the first step, you run the DFC on the graph, and then as you finish visiting each node and all its descendants, you add it to the stack or like a list. And the order in which all nodes are added to this stack is very important because it helps you to identify the component of the next phase. And the second step we use here is to perform the DFC on the transposed graph. So here, this is where we create a transposed or a reverse version of the original graph that we had. And this means you basically have to take the original graph and then reverse the direction of all its edges, and then you run the second DFC on the transposed graph, but you visit in the order determined by the stack from the first phase. And each time you start a new DFC from a node on the stack, you have found a newly strongly connected component. For example, in the given example that we have here, we're going to perform the DFC on this original directed graph, and the goal here is to visit every node, and as we finish visiting a node and all its descendants, we push it into a stack. So a good starting point is 0. So we start from 0, we go to 1, we go to 2, we go to 3, we go to 4, go to 5, and the unvisited node, we finish with it and add it to our stack. So our stack basically has 5. And now we're going to backtrack to 4 and go to 6. Go to 7. Since 7 has no outgoing edges to unvisited nodes, we finish with it and add it to our stack. So now our stack has 2 elements, 5 and 7. So we're going to backtrack to 6. So it has no other unvisited neighbors. We finish with it as well. We add it to the stack. We backtrack to 4. We add it to the stack. 3, 2, 1, and 0. And now we're done with the DFC. So now we're going to reverse the direction of all edges in the original graph to get the transpose of the graph. So next we're going to run a new DFC to the transposed graph. So now we're going to pop 5, start the DFC from 5 on the transposed graph. And here the only node reachable from 5 is 4, but 4 is not reachable from 5 in the transposed graph. So the only node reachable from 5 is the transposed graph. In the transposed graph is 4. But that is not correct. There is no outgoing edges from 5 in the transposed graph. So the first strongly connected component is just 5. And now we're going to pop 7. So from the stack, we start the DFC from 7. And the only reachable node from 7 is 6. So we visit 7 and 6. So these two nodes are strongly connected components. So we pop 6 from the stack, and it has already been visited, so we're going to ignore it. And then we pop 4 from the stack, and we start the DFC from 4, and the only reachable node is 3. So from 3 we can reach 2, and from 2 we can reach 1. From 1 we can reach 0. From 0 we can reach 1. From 1 we can reach 2. So from 4 we can reach 3, 2, 1, and 0, and all these are mutually reachable from each other within this group. So these form a strongly connected component. So the rest of the nodes on the stack 3, 2, 1, 0 have all been visited in the previous steps. So now our strongly connected components are a set of 5, a set of 6 and 7, and a set of 0, 1, 2, 3, and 4. So this brings us to the end of this presentation. Like, comment, and